An acid is a chemical substance whose aqueous solutions are characterized by a sour taste, the ability to turn blue litmus red, and the ability to react with bases and certain metals to form salts. Aqueous solutions of acids have a pH of less than 7. A lower pH means a higher acidity, and thus a higher concentration of hydrogen ions in the solution. Chemicals or substances having the property of an acid are said to be acidic. Common examples of acids include hydrochloric acid, acetic acid, sulfuric acid, and tartaric acid. As these examples show, acids can be solutions or pure substances, and can be derived from solids, liquids, or gases. Strong acids and some concentrated weak acids are corrosive, but there are exceptions such as carboranes and boric acid. There are three common definitions for acids: the Aeneas definition, the Bryan-Sted definition, and the Lewis definition. The Aeneas definition defines acids as substances which increase the concentration of hydrogen ions, or more accurately, hydronium ions, when dissolved in water. The Bryan-Sted definition is an expansion: an acid is a substance which can act as a proton donor. By this definition, any compound which can easily be deprotonated can be considered an acid. Examples include alcohols and amines which contain OH or NH fragments. A Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. Examples of Lewis acids include all metal cations, and electron-deficient molecules such as boron trifluoride and aluminium trichloride. Definitions and concepts. Modern definitions are concerned with the fundamental chemical reactions common to all acids. Most acids encountered in everyday life are aqueous solutions, or can be dissolved in water, so the Aeneas and Bryan-Sted definitions are the most relevant. The Bryan-Sted definition is the most widely used definition. Unless otherwise specified, acid-base reactions are assumed to involve the transfer of a proton from an acid to a base. Hydronium ions are acids according to all three definitions. Interestingly, although alcohols and amines can be Bryan-Sted acids, they can also function as Lewis bases due to the lone pairs of electrons on their oxygen and nitrogen atoms. Aeneas acids. The Swedish chemist Svante Aeneas attributed the properties of acidity to hydrogen ions or protons in 1884. An Aeneas acid is a substance that, when added to water, increases the concentration of H+ ions in the water. Note that chemists often write H+, Ac, and refer to the hydrogen ion when describing acid-base reactions, but the free hydrogen nucleus, a proton, does not exist alone in water, it exists as the hydronium ion, H3O+. Thus, an Aeneas acid can also be described as a substance that increases the concentration of hydronium ions when added to water. This definition stems from the equilibrium dissociation of water into hydronium and hydroxide ions, H2O, L, plus H2O, L, H3O+, Ac, plus OA, Ac. In pure water the majority of the molecules are H2O, but the molecules are constantly dissociating and reassociating, and at any time a small number of the molecules are hydronium and an equal number are hydroxide. Because the numbers are equal, pure water is neutral. An Aeneas base, on the other hand, is a substance which increases the concentration of hydroxide ions when dissolved in water, hence decreasing the concentration of hydronium. The constant association and dissociation of H2O molecules forms an equilibrium in which any increase in the concentration of hydronium is accompanied by a decrease in the concentration of hydroxide. Thus an Aeneas acid could also be said to be one that decreases hydroxide concentration, with an Aeneas base increasing it. The reason that pHs of acids are less than 7 is that the concentration of hydronium ions is greater than 10^7 moles per liter. Since pH is defined as the negative logarithm of the concentration of hydronium ions, acids thus have pHs of less than 7. Bryan-Sted acids. While the Aeneas concept is useful for describing many reactions, it is also quite limited in its scope. In 1923, chemists Johannes Nicolaus Brian Sted and Thomas Martin Lowry independently recognized that acid-base reactions involve the transfer of a proton. A Brian Sted Lowry acid is a species that donates a proton to a Brian Sted Lowry base. Brian Sted Lowry acid base theory has several advantages over Aeneas theory. Consider the following reactions of acetic acid, the organic acid that gives vinegar its characteristic taste: CH, 3COOH plus H, 2OCH, 3COA plus H, 3O plus, CH, 3COOH plus NH, 3CH, 3COA plus NH plus, 4. Both theories easily describe the first reaction. CH3COOH acts as an Aeneas acid because it acts as a source of H3O+ when dissolved in water, and it acts as a Brian Sted acid by donating a proton to water. In the second example, CH3COOH undergoes the same transformation, in this case donating a proton to ammonia, but cannot be described using the Aeneas definition of an acid because the reaction does not produce hydronium. Brian Sted Lowry theory can also be used to describe molecular compounds, whereas Aeneas acids must be ionic compounds. Hydrogen chloride and ammonia combine under several different conditions to form ammonium chloride, NH4Cl. In aqueous solution, HCl behaves as hydrochloric acid and exists as hydronium and chloride ions. The following reactions illustrate the limitations of Aeneas's definition: H3O plus, Ac, plus clap, Ac, plus NH3 clap, Ac, plus NH4 plus, Ac, plus H2O, HCl, benzene, plus NH3, benzene, ANH4Cl, S, HCl, G, plus NH3, G, ANH4Cl, S. As with the acetic acid reactions, both definitions work for the first example, where water is the solvent and hydronium ion is formed by the HCl solute. The next two reactions do not involve the formation of ions but are still proton transfer reactions. In the second reaction, hydrogen chloride and ammonia react to form solid ammonium chloride in a benzene solvent, and in the third, gaseous HCl and NH3 combine to form the solid. Lewis acids. A third concept was proposed in 1923 by Gilbert N. Lewis, which includes reactions with acid-base characteristics that do not involve a proton transfer. A Lewis acid is a species that accepts a pair of electrons from another species. In other words, it is an electron pair acceptor. Brian Sted acid-base reactions are proton transfer reactions, while Lewis acid-base reactions are electron pair transfers. All Brian Sted acids are also Lewis acids, but not all Lewis acids are Brian Sted acids. Contrast the following reactions which could be described in terms of acid-base chemistry. In the first reaction, a fluoride ion, Fa, gives up an electron pair to boron trifluoride to form the product tetrafluoroborate. Fluoride loses a pair of valence electrons because the electrons shared in the Bar-F bond are located in the region of space between the two atomic nuclei and are therefore more distant from the fluoride nucleus than they are in the lone fluoride ion. Bf3 is a Lewis acid because it accepts the electron pair from fluoride. This reaction cannot be described in terms of Brian Sted theory because there is no proton transfer. The second reaction can be described using either theory. A proton is transferred from an unspecified Brian Sted acid to ammonia, a Brian Sted base. Alternatively, ammonia acts as a Lewis base and transfers a lone pair of electrons to form a bond with a hydrogen ion. The species that gains the electron pair is the Lewis acid. For example, the oxygen atom NH3O+ gains a pair of electrons when one of the Ha-O bonds is broken and the electrons shared in the bond become localized on oxygen. Depending on the context, a Lewis acid may also be described as an oxidizer or an electrophile. Dissociation and equilibrium. Reactions of acids are often generalized in the form HAH++ or, where HA represents the acid and or is the conjugate base. Acid-base conjugate pairs differ by one proton, and can be interconverted by the addition or removal of a proton. Note that the acid can be the charged species and the conjugate base can be neutral, in which case the generalized reaction scheme could be written as HA plus H plus A. In solution there exists an equilibrium between the acid and its conjugate base. The equilibrium constant K is an expression of the equilibrium concentrations of the molecules or the ions in solution. Brackets indicate concentration, such that H2O means the concentration of H2O. The acid dissociation constant Ca is generally used in the context of acid-base reactions. The numerical value of Ca is equal to the product of the concentrations of the products divided by the concentration of the reactants, where the reactant is the acid and the products are the conjugate base and H+. The stronger of two acids will have a higher Ca than the weaker acid. The ratio of hydrogen ions to acid will be higher for the stronger acid, as the stronger acid has a greater tendency to lose its proton. Because the range of possible values for Ca spans many orders of magnitude, a more manageable constant, pKa is more frequently used, where pKa equals log 10 Ca. Stronger acids have a smaller pKa than weaker acids. Experimentally determined pKa at 25 degrees in aqueous solution are often quoted in textbooks and reference material. Nomenclature: in the classical naming system, acids are named according to their anions. That ionic suffix is dropped and replaced with a new suffix, according to the table below. For example, HCl has chloride as its anion, so the ide suffix makes it take the form hydrochloric acid. In the IUPAC naming system, aqueous is simply added to the name of the ionic compound. Thus, for hydrogen chloride, the IUPAC name would be aqueous hydrogen chloride. The prefix hydro is added only if the acid is made up of just hydrogen and one other element. Classical naming system: acid strength. The strength of an acid refers to its ability or tendency to lose a proton. A strong acid is one that completely dissociates in water. In other words, 1 mole of a strong acid HA dissolves in water, yielding 1 mole of H+ and 1 mole of the conjugate base, and none of the protonated acid HA. In contrast, a weak acid only partially dissociates, and at equilibrium both the acid and the conjugate base are in solution. Examples of strong acids are hydrochloric acid, hydriodic acid, hydrobromic acid, perchloric acid, nitric acid and sulfuric acid. In water each of these essentially ionizes 100%. The stronger an acid is, the more easily it loses a proton, H+. Two key factors that contribute to the ease of deprotonation are the polarity of the Ha-A bond and the size of atom A, which determines the strength of the Ha-A bond. Acid strengths are also often discussed in terms of the stability of the conjugate base. Stronger acids have a larger Ca and a more negative pKa than weaker acids. Sulphonic acids, which are organic oxyacids, are a class of strong acids. A common example is toluenesulphonic acid. Unlike sulfuric acid itself, sulphonic acids can be solids. In fact, polystyrene functionalized into polystyrene sulfonate is a solid strongly acidic plastic that is filterable. Superacids are acids stronger than 100% sulfuric acid. Examples of superacids are fluoroantimonic acid, magic acid and perchloric acid. Superacids can permanently protonate water to give ionic, crystalline hydronium salts. They can also quantitatively stabilize carbocations. While Ca measures the strength of an acid compound, the strength of an aqueous acid solution is measured by pH, which is an indication of the concentration of hydronium in the solution. The pH of a simple solution of an acid compound in water is determined by the dilution of the compound in the compound's Ca. Chemical characteristics: monoprotic acids. Monoprotic acids are those acids that are able to donate one proton per molecule during the process of dissociation as shown below. HA, Ac, plus H2O, L, H3O plus, Ac, plus or, Ac, AAA Ca. Common examples of monoprotic acids in mineral acids include hydrochloric acid and nitric acid. On the other hand, for organic acids the term mainly indicates the presence of one carboxylic acid group, and sometimes these acids are known as monocarboxylic acid. Examples in organic acids include formic acid, acetic acid and benzoic acid. Polyprotic acids, also known as polyprotic acids, are able to donate more than one proton per acid molecule, in contrast to monoprotic acids that only donate one proton per molecule. Specific types of polyprotic acids have more specific names, such as diprotic acid and triprotic acid. A diprotic acid can undergo one or two dissociations depending on the pH. Each dissociation has its own dissociation constant, Ca1 and Ca2. H2A, Ac, plus H2O, L, H3O plus, Ac, plus HOR, Ac, Aa Ca1, HOR, Ac, plus H2O, L, H3O plus, Ac, plus A2A, Ac, Aa Ca2. The first dissociation constant is typically greater than the second. That is, Ca1, Ca2. For example, sulfuric acid can donate one proton to form the bisulfate anion, for which Ca1 is very large. Then it can donate a second proton to form the sulfate anion, wherein the Ca2 is intermediate strength. The large Ca1 for the first dissociation makes sulfuric a strong acid. In a similar manner, the weak and stable carbonic acid can lose one proton to form bicarbonate anion and lose a second to form carbonate anion. Both Ca values are small, but Ca1, Ca2. A triprotic acid can undergo 1, 2, or 3 dissociations and has 3 dissociation constants, where Ca1, Ca2, Ca3. H3A, Ac, plus H2O, L, H3O plus, Ac, plus H2O, Ac, Aa Ca1, H2O, Ac, plus H2O, L, H3O plus, Ac, plus Ha2A, Ac, Aa Ca2, Ha2A, Ac, plus H2O, L, H3O plus, Ac, plus A3A, Ac, Aa Ca3. An inorganic example of a triprotic acid is orthophosphoric acid, usually just called phosphoric acid. All 3 protons can be successively lost to yield H2PO4, then HPO42, and finally PO43, the orthophosphate ion, usually just called phosphate. An organic example of a triprotic acid is citric acid, which can successively lose 3 protons to finally form the citrate ion. Even though the positions of the protons on the original molecule may be equivalent, the successive Ca values will differ since it is energetically less favorable to lose a proton if the conjugate base is more negatively charged. Although the subsequent loss of each hydrogen ion is less favorable, all of the conjugate bases are present in solution. The fractional concentration, I plus or minus, for each species can be calculated. For example, a generic diprotic acid will generate 3 species in solution, H2A, HA, and A2. The fractional concentrations can be calculated as below when given either the pH or the concentrations of the acid with all its conjugate bases. A plot of these fractional concentrations against pH, for given K1 and K2, is known as Occurrence plot. A pattern is observed in the above equations and can be expanded to the general N-protic acid that has been deprotonated I times. Where Ko equals 1 and the other K terms are the dissociation constants for the acid. Neutralization. Neutralization is the reaction between an acid and a base, producing a salt and neutralized base. For example, hydrochloric acid and sodium hydroxide form sodium chloride and water, HCl, Ac, plus NaO, Ac, H2O, L, plus NaCl, Ac. Neutralization is the basis of titration, where a pH indicator shows equivalence point when the equivalent number of moles of a base have been added to an acid. It is often wrongly assumed that neutralization should result in a solution with penthouse 700, which is only the case with similar acid and base strengths during a reaction. Neutralization with a base weaker than the acid results in a weakly acidic salt. An example is the weakly acidic ammonium chloride, which is produced from the strong acid hydrogen chloride and the weak base ammonia. Conversely, neutralizing a weak acid with a strong base gives a weakly basic salt, for example sodium fluoride from hydrogen fluoride and sodium hydroxide. Weak acid weak base equilibrium. In order for a protonated acid to lose a proton, the pH of the system must rise above the pKa of the acid. The decreased concentration of H+ in that basic solution shifts the equilibrium towards the conjugate base form. In lower pH solutions, there is a high enough H+ concentration in the solution to cause the acid to remain in its protonated form. Solutions of weak acids and salts of their conjugate bases form buffer solutions. Applications of acids. There are numerous uses for acids. Acids are often used to remove rust and other corrosion from metals in a process known as pickling. They may be used as an electrolyte in a wet cell battery, such as sulfuric acid in a car battery. Strong acids, sulfuric acid in particular, are widely used in mineral processing. For example, phosphate minerals react with sulfuric acid to produce phosphoric acid for the production of phosphate fertilizers, and zinc is produced by dissolving zinc oxide into sulfuric acid, purifying the solution and electrowinning. In the chemical industry, acids react in neutralization reactions to produce salts. For example, nitric acid reacts with ammonia to produce ammonium nitrate, a fertilizer. Additionally, carboxylic acids can be esterified with alcohols, to produce esters. Acids are used as additives to drinks and foods, as they alter their taste and serve as preservatives. Phosphoric acid, for example, is a component of cola drinks. Acetic acid is used in day-to-day life as vinegar. Carbonic acid is an important part of some cola drinks and soda. Citric acid is used as a preservative in sauces and pickles. Tartaric acid is an important component of some commonly used foods like unripened mangoes and tamarind. Natural fruits and vegetables also contain acids. Citric acid is present in oranges, lemon and other citrus fruits. Oxalic acid is present in tomatoes, spinach, and especially in carambola and rhubarb. Rhubarb leaves and unripe carambolas are toxic because of high concentrations of oxalic acid. Ascorbic acid is an essential vitamin for the human body and is present in such foods as amla, lemon, citrus fruits, and guava. Certain acids are used as drugs. Acetylsalicylic acid is used as a painkiller and for bringing down fevers. Acids play important roles in the human body. The hydrochloric acid present in the stomach aids in digestion by breaking down large and complex food molecules. Amino acids are required for synthesis of proteins required for growth and repair of body tissues. Fatty acids are also required for growth and repair of body tissues. Nucleic acids are important for the manufacturing of DNA and RNA and transmitting of traits to offspring through genes. Carbonic acid is important for maintenance of pH equilibrium in the body. Acid catalysis. Acids are used as catalysts in industrial and organic chemistry. For example, sulfuric acid is used in very large quantities in the alkylation process to produce gasoline. Strong acids, such as sulfuric, phosphoric and hydrochloric acids also affect dehydration and condensation reactions. In biochemistry, many enzymes employ acid catalysis. Biological occurrence. Many biologically important molecules are acids. Nucleic acids, which contain acidic phosphate groups, include DNA and RNA. Nucleic acids contain the genetic code that determines many of an organism's characteristics, and is passed from parents to offspring. DNA contains the chemical blueprint for the synthesis of proteins which are made up of amino acid subunits. Cell membranes contain fatty acid esters such as phospholipids. An I+ or minus amino acid has a central carbon which is covalently bonded to a carboxyl group, an amino group, a hydrogen atom and a variable group. The variable group, also called the A group or side chain, determines the identity and many of the properties of a specific amino acid. In glycine, the simplest amino acid, the A group is a hydrogen atom, but in all other amino acids it contains one or more carbon atoms bonded to hydrogens, and may contain other elements such as sulfur, oxygen or nitrogen. With the exception of glycine, naturally occurring amino acids are chiral and almost invariably occur in the L configuration. Peptidoglycan, found in some bacterial cell walls, contains some D amino acids. At physiological pH, typically around 7, Free amino acids exist in a charged form, where the acidic carboxyl group loses a proton and the basicum group gains a proton. The entire molecule has a net neutral charge and is as Zwitterian, with the exception of amino acids with basic or acidic side chains. Aspartic acid, for example, possesses one protonated amine and two deprotonated carboxyl groups, for a net charge of a 1 at physiological pH. Fatty acids and fatty acid derivatives are another group of carboxylic acids that play a significant role in biology. These contain long hydrocarbon chains and a carboxylic acid group on one end. The cell membrane of nearly all organisms is primarily made up of a phospholipid bilayer, a missile of hydrophobic fatty acid esters with polar, hydrophilic phosphate head groups. Membranes contain additional components, some of which can participate in acid-base reactions. In humans and many other animals, hydrochloric acid is a part of the gastric acid secreted within the stomach to help hydrolyze proteins and polysaccharides, as well as converting the inactive proenzyme, pepsinogen into the enzyme, pepsin. Some organisms produce acids for defense. For example, ants produce formic acid. Acid-base equilibrium plays a critical role in regulating mammalian breathing. Oxygen gas drives cellular respiration, the process by which animals release the chemical potential energy stored in food, producing carbon dioxide as a byproduct. Oxygen and carbon dioxide are exchanged in the lungs, and the body responds to changing energy demands by adjusting the rate of ventilation. For example, during periods of exertion the body rapidly breaks down stored carbohydrates and fat, releasing CO2 into the bloodstream. In aqueous solutions such as blood, CO2 exists in equilibrium with carbonic acid and bicarbonate ion, CO2 plus H2O H2CO3H plus HCO3. It is the decrease in pH that signals the brain to breathe faster and deeper, expelling the excess CO2 and resupplying the cells with O2. Cell membranes are generally impermeable to charged or large, polar molecules because of the lipophilic fatty acyl chains comprising their interior. Many biologically important molecules, including a number of pharmaceutical agents, are organic weak acids which can cross the membrane in their protonated, uncharged form but not in their charged form. For this reason the activity of many drugs can be enhanced or inhibited by the use of antacids or acidic foods. The charged form, however, is often more soluble in blood and cytosol, both aqueous environments. When the extracellular environment is more acidic than the neutral pH within the cell, certain acids will exist in their neutral form and will be membrane-soluble, allowing them to cross the phospholipid bilayer. Acids that lose a proton at the intracellular pH will exist in their soluble, charged form and are thus able to diffuse through the cytosol to their target. Ibuprofen, aspirin and penicillin are examples of drugs that are weak acids. Common acids, mineral acids, hydrogen halides and their solutions, hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydrolodic acid, halogen oxyosides, hypochlorous acid, chlorous acid, chloric acid, perchloric acid, and corresponding compounds for bromine and iodine, sulfuric acid, fluorosulfuric acid, nitric acid, phosphoric acid, fluoroantimonic acid, fluoroboric acid, hexafluorophosphoric acid, chromic acid, boric acid, sulphonic acids, methanosulphonic acid, ethanosulphonic acid, benzenosulphonic acid, ketoluenesulphonic acid, trifluoromethanosulphonic acid, polystyrene sulphonic acid SO3H, N, carboxylic acids, acetic acid, citric acid, formic acid, gluconic acid HOCH2, CHOH, 4COOH, lactic acid, oxalic acid, tartaric acid, halogenated carboxylic acids, halogenation at alpha position increases acid strength, so that the following acids are all stronger than acetic acid: fluoroacetic acid, trifluoroacetic acid, chloroacetic acid, dichloroacetic acid, trichloroacetic acid, vinylogous carboxylic acids. Normal carboxylic acids are the direct union of a carbonyl group and a hydroxy group. In vinylogous carboxylic acids, A carbon-carbon double bond separates the carbonyl and hydroxyl groups. Ascorbic acid, nucleic acids, deoxyribonucleic acid, ribonucleic acid, references. Listing of strengths of common acids and bases, IUPAC Gold Book, Acid, Zumdahl, Chemistry, 4th edition. Ebbing, D.D., and Gammon, S.D. General Chemistry. Boston, Massachusetts, Houghton Mifflin. ISBN 0-618-51177-6, Pavia, D.L., Lampman, G.M., and Chris, G.S. Organic Chemistry Volume 1, Organic Chemistry 351. Mason, Ohio, Senage Learning. ISBN 0-7593-4727-1, External links, Science Aid, Acids and Bases Information for High School Students, Kurtopot, Acid-Base Equilibria Diagrams, pH Calculation and Titration Curves Simulation and Analysis Freeware, a Summary of the Properties of Acids for the Beginning Chemistry Student, the Union ECE Convention on Long-Range Transboundary Air Pollution, Chem 106 Acidity Concepts.